So all I'm going to talk about right now is essentially different types of nucleophiles, some new ones that we haven't maybe seen before. One's called Grignards, hydrides, and organolithiums. So Grignards are carbons that are bonded to magnesium. Hydrides are sources of H-, and organolithiums are carbons that are bonded to lithium. So the reason why this is interesting is because even though, of course, this bond looks just like a covalent bond, as does this bond, we know when carbon's bonded to sodium, lithium, potassium, and magnesium, that's not a covalent bond. That's actually a ionic bond, right? So this is a good source. We're going to talk a lot about carbon nucleophiles. So the nucleophiles we're going to talk about are C- and H-. So these are really reactive nucleophiles, right? Carbon and hydrogen don't like to have a negative charge. They're very reactive nucleophiles. Okay, so before we get too far along, let's talk about, we're going to talk about first making Grignards. How do we actually make Grignards? There's actually kind of neat ways to think about electrophiles and nucleophiles again. So if you all have been thinking about, so we already know a Grignard, which is up here, is a carbon with a negative charge bonded to a magnesium. So it's a really good carbon nucleophile. But it didn't always start out that way. That carbon actually was electrophilic at first. So these come from alkyl bromides. So carbon bonded to bromine. And what's going to happen is a metal is actually going to be inserted. We call that an oxidative addition. It's going to be inserted. It's going to add. The metal is going to be oxidized, hence oxidative addition. And it's actually going to be a homolytic process. So we're going to practice our radical arrows now. So how does this happen? So let's draw our electrons in there. We know the product is going to be what? We know it's going to be this. All right? So one of the red electrons is going to be there. One's going to be there. Black electrons there. Black electrons there. So how does this happen? How many electrons in a bond? 2. So what happens, this red electron and this one black electron from magnesium, 0. Now this is magnesium. The charge on magnesium is 0. Here it's magnesium 2, or we say 2 plus. So the magnesium here donates 1 electron. The carbon-bromine bond, which is reactive because it's polar, also donates 1 electron. That forms this bond right here, 2 electrons in a bond. Another single electron from magnesium and a single electron from this carbon-bromine bond react and form another carbon-bromine bond. We say this is oxidized because the metal is actually giving up electrons, right? If you saw a metal bonded to carbon, who do you think or metal bonded to bromine, who owns the electrons? Who's more electronegative? The bromine is. And even a metal bonded to carbon, right? Metals are really electropositive. They're really delta plus. A carbon bonded to magnesium is also going to have a negative charge on those electrons. So the metal we could say is 2 plus. That's how we make the Grignard, right? We can do it all sorts of ways. Any sort of alkyl bromides we can do this, right? So you can imagine same thing down here below. You could maybe I'll allow you all to practice this right now to see if you can do this with arrows. So when we do this, we generate a good nucleophile, and that can be used to react with different things. All right, so if I wanted to show how that reacts, I could show it reacting with a ketone. So the Grignard is going to be my nucleophile or electrophile. Nucleophile has a carbon with a negative charge. What part of the ketone there is electrophilic? The carbon of the carbonyl, right? This carbon bonded to the oxygen. So I draw the electrons in. We do that addition step. Right? This is where numbering our carbons becomes really important. A lot of times people will lose a carbon along the way. Don't lose your carbons. That's our first addition. Then we do a protonation, the second step. Right? We made a tetrahedral intermediate. Do we have any good leaving groups? Nope. No good leaving groups. Nothing that would want a negative charge. That's what I say. Is there any stable leaving groups? Nope. So the second step would just be right? So this was step 1. Step 2 would involve H+. All right, so completely different new step. And we'll do protonation. You'll see that we've made an alcohol. Right? We're learning about alcohol synthesis in this unit. So quickly I want to add in, I think this just fits here. Organolithiums just kind of fit here. I'm not going to ask you how they're made. So organolithiums you can just kind of have already. So if you have something like this, organolithium, you've seen this before. But all it is a carbon nucleophile. So really this is equal to this. And this will react the same way. Right? This will react like a Grignard reacts. Now be careful. It's always looking for the best electrophile. It's always looking for the best electrophile. So be careful when there's things like OHs, right? Or acids around. Grignards and organolithiums like to go for those hydrogens too. They can act like a base, right? A Bronsted base, not just as a nucleophile. So be careful with that. So to show specifically what I mean by that, the Grignards being compatible or the organolithiums being compatible. So let me show you one quick example. Is if I had a Grignard, say the one I had before, right? This is a carbanion, really it's a carbon with a negative charge here, and magnesium has a plus charge. If the ketone I was reacting with, let's say it also had an OH, that won't work because essentially the problem is going to be is this Grignard is a really good nucleophile and it's going to want to react with, it's going to want to react here, but it's also going to want to react here, and that's going to shut this reaction down, right? So just like we used H plus before to kind of stop this reaction, the second step, if we have OHs, NHs, right, if we use polar protic solvents, right, you can't use these solvents like an alcohol solvent, right, that won't work for a Grignard because our C minus is also going to react with the H. You see a lot of sampling problems like that. So how do hydrides fit in this? How do we get these things like H minus, a hydrogen with a negative charge? So these fit in. There's two major hydrides we use. There's sodium borohydride, and there's lithium aluminum hydride. So these are sources of H minus, right? These are sources of H minus. A hydrogen nucleophile, hydride. Sometimes you'll see lithium aluminum hydride written as LAH, just so you know that. Let's think about the actual Lewis dot structure of these. Where's the plus charge? Where's the minus charge? So what we'll see here, we know sodium has a plus charge. We know lithium has a plus charge. And the tricky part is boron has a minus charge and aluminum has a minus charge. But where is all the electron density at? Where is it actually electronegative? It's actually electronegative out at the hydrogens, right? It's out of the hydrogens. Now here's a question. What's more reactive, a BH or aluminum H? Let's look at the size. So here's little boron. Here's H. Not drawn to scale. There's aluminum. There's H. Which one has more orbital overlap, BH or aluminum H? BH. Right? Do you see this? This is a more stable bond. This is less reactive than this because aluminum's larger. That's going to make this more reactive. That's important. Lithium aluminum hydride is more reactive than sodium borohydride. Lithium aluminum hydride is a more reactive nucleophile. It will react with something that's less reactive. This will react with esters. And of course, esters are less reactive than ketones. Right? So this becomes important. This is that selectivity a little bit here. Good. So how does this look if you actually need to react with an electrophile? So for right now, the easiest thing to do if you see sodium borohydride, just draw out an H minus. Same with lithium aluminum hydride. Just draw out an H minus. So draw a hydrogen with a lone pair and have it react. So now your hydrogen's your nucleophile. It's going to react there. Does that addition. And then you can do step 2 would be a protonation. And what have you made? You've made another alcohol with a new nucleophile hydride.